Hello, everyone. Welcome back to the AAS YouTube channel, and this is the good stuff. This is the AAS Journal Author Series, and I'm super happy to have Amir Jafari with us today. Hi, Amir.
Hi, Frank. How are you doing?
I'm doing okay. We're going to be of order 110F in Phoenix, Arizona today, so it'll be nice and toasty. Probably a good thing to take a siesta in the afternoon when it gets really hot. So maybe I'll be doing that.
Absolutely.
Where are you at?
I'm at Rockville near DC.
Oh, okay.
It is a little warm here, but not too bad.
How's the humidity?
Humidity is almost like Baltimore, so it is humid.
Mm-hmm. So you got the summer humidity going.
Yeah.
But no locusts this year. No.
No.
Not this year. Cool. So is John Hopkins, are they planning on opening in the fall?
I don't know. I'm not sure. So probably I shouldn't say anything about this because it's kind of complicated.
Yeah.
And it's every day all plans are changing, and I'm not following up with the news. So I'm not sure. I don't know.
Same thing at ASU. Supposedly we're opening August 21st, but who knows? Yeah. So what do you like to do for research, Amir?
Well, my background, actually, my training is basically my training is mathematical physics. Training in mathematical physics. I was working on strongly coupled quantum field theories and representation theory, stuff like that.
Yep.
Then I switched to astrophysics, working with Ethan Vishniak at Hopkins, then at McMaster back in Canada. And we started working on astrophysical magnetic fields. So I got interested in large scale magnetic fields, and like dynamo theories and basically reconnection. Which is actually very related to the problem of turbulence, because astrophysical fluids are basically, in general, all of them are turbulent. And so I've been working on turbulent magnetic fields. This is the short answer. But because of my training, I'm mostly interested in mathematical development of the problems, which is really hard in astrophysics. For example, if you consider an accretion disk, for example,
right?
Then, it's really hard to write down a boundary value problem for the magnetic field evolution in accretion disk. So you should be careful. But there are many interesting problems and related to turbulent magnetic fields. One of them is the reconnection, which is actually very ubiquitous in astrophysical fluids, accretion disks, stars, solar wind, everywhere. So currently I'm working on topological properties of magnetic fields and turbulent fluids, which is basically related to reconnection, physically speaking.
Cool. In fact, we're going to take a look at one of these lovely research notes of yours. So let's go ahead and put that up. So we're going to take a look at nanoflare theory and stochastic reconnection. Amir, take us away.
Okay, a long time ago, I guess 70s and 80s, Eugene Parker introduced this concept of the theory of nanoflare theory and microflare theory. There are different names of this phenomenon. It is basically, it's related to coronal heating, solar coronal heating problem. Parker suggested that if you have a turbulent fluid, like the solar corona, you can imagine that magnetic field is very tangled in space. So we're going to have many reconnection events at different regions in space, which basically means, in a plain language, that you are having simultaneous reconnection events at different regions in space. One of these events annihilates magnetic field, so generates heat, and also converts magnetic energy to kinetic energy, but that's not important here. We're interested in heating process involved in these reconnection events. So the idea was that, well, in the solar corona, this happens all the time. You have many reconnection events, many annihilation events. So these events produce heat, and this heat is responsible for the extra, heating process in the solar corona. That's the idea. This is Parker's theory, nanoflare theory.
Yep.
Now, in 1999, Alex Lazarian and Ethan Vishniak put forward a basically, it's a complicated process, but it's a model for magnetic reconnection. Well, first of all, I should say what is magnetic reconnection, basically.
Okay.
If you have a large shear in a region of plasma, say, or highly conducting fluid, then because of these magnetic shears, you're going to have a current sheet, electric current. So this configuration is not stable, and magnetic field will change its topology basically very spontaneously. And changing topology will generate jets of fluid in space. So this is reconnection. But in turbulence, you don't have these nice topologies for magnetic field. Everything is complicated and chaotic. And basically what turbulence does to the magnetic field is that it tangles the magnetic field, generating many local reconnection events, small scale reconnection events. So this is the essence of stochastic reconnection. And if these events are kind of in phase, you're going to have a larger scale reconnection event.
All right.
Many simultaneous small scale reconnection events give rise to a larger scale observable reconnection. This is a stochastic reconnection. Now, recently in a series of papers, we have approached this stochastic reconnection using, you can scroll down so we can see the first equation in this node. If you go, over here, equation number 1. Recently, we have formulated a statistical formalism which can be used to study all sorts of magnetic field topologies and magnetic field evolution actually in turbulent or in laminar flows. The basic idea here is a definition given by equation 1 here, which basically defines a level of tanglement or level of spatial complexity for a vector field. If you have any given vector field, say in 3 dimensions, like a magnetic field, you can ask how tangled the field is in space. I mean, the geometric sense, what is the level of complexity of the field? So for a magnetic field, for example, if you have a very laminar flow, the magnetic field would be kind of smooth in space. So in that case, we define this complexity or stochasticity level to be 0. But as the turbulence tangles the field, then this complexity level increases. It's normalized, actually. You can see this factor of 1/2 over there, which means it's a number between 0 and 1. So anyway, this function, S of t, gives you a quantified, measure of magnetic complexity. So it turns out that as turbulence proceeds, magnetic field complexity increases. And this means that at different locations in space, you're going to have magnetic field lines which produce actually large, strong shears. So basically, I don't know if I could share my screen, which I believe I can, and I would show you a nice schematic of this configuration. I don't know, can I share my screen or?
Sure. Let me, I need to get out of screen sharing, so I'm going to stop my screen share. I'm going to give you permission to share your screen, and you should be able to share your screen.
So share screen over here. Okay, can you see the speaker over here? And watch it. this one. When you have a laminar flow, like this upper panel over here, magnetic field is kind of smooth and it has a low complexity. But in a fully turbulent fluid, you're going to have this kind of configuration for the magnetic field, the lower panel in this figure, which means you have a highly complex magnetic field. So you can.
Let me ask a question.
Yes, sure.
So just to ground myself in some familiar territory. So would a dipole magnetic field that would have a complexity of 0?
Or not strict 0, but it would be very small.
Okay.
But what is important here, by the way, is the scale you are looking at the field. If you look at a dipole magnetic field at smaller scales, it's basically very smooth. You
Right.
see this kind of, the upper level, upper panel in this figure. It would be
Okay.
something like this, even smoother. But at larger scales, you have, what's important here, I don't have time to go through this, but what's important here is the distinction between the curvature of the magnetic field and also the curvature of a small scale magnetic field.
Okay.
Yes, basically at smaller scales for a dipole, we have 0 complexity.
Okay.
Anyway, in turbulence, you have this lower panel. This is a schematic, so it's not a mathematically precise picture, but it gives you an idea of what we are talking about. A high complexity, you have this kind of very complex and chaotic, magnetic field lines and space. So it's expected that you're going to have these local current sheets. I mean, because turbulence entangles, because it stretches and bends the magnetic field, it's going to create local regions in which you have anti-parallel, for example, magnetic field lines. So it means that you're going to have local reconnection events.
Mm-hmm. Yep.
Now, what happens when you have reconnection? It produces jets of fluid. When you have jets of fluid, very eruptive fluid motions, the complexity level of the velocity field will increase. So you can define the same concept for the velocity field. So if you look at these complexities, these functions as time series, for example, one for the magnetic field, another one for the velocity field, then you will see that as magnetic complexity increases and reaches a maximum, then the field reconnects, and then you have an increase in the complexity of the velocity field. So I can stop sharing my screen, I guess, at this point.
Okay, and I will put my back.
Okay.
So there's your
equation 1. It means that you can look at this problem statistically and study the complexity level, and so the energy of magnetic field and velocity field, and similar quantities. Now, if you scroll down on this page, this figure shows how this magnetic complexity level changes with time. Basically, the blue one is the time derivative of the magnetic complexity, and the red dashed curve is the magnetic dissipation rate, the rate at which magnetic energy is converted to thermal energy. And you see that these time series or these functions are very correlated. It means that when you have a large change in magnetic complexity, you have also dissipated magnetic energy very strongly. So when you look at, this is from a numerical simulation, which is stored at Johns Hopkins turbulence database. You can do the same calculation numerically with any actually MHD simulation, and it shows you that the complexity level is strongly correlated with the dissipation rate of magnetic energy, which is basically Parker's idea. When you have a very entangled magnetic field in space, because of the generation of these local current sheets, magnetic energy would be dissipated and you're going to have heat as a result. So this is a statistical reformulation of Parker's idea, which at the same time shows that Parker's nanoflare theory is related to the stochastic reconnection put forward by Alex Mazarian and Ethan Vishniak long time ago.
my eyes want to make a connection between the two blue peaks, which would be the rate of change of the complexity with time, and they're sort of phase lagged, or they're lagged
Yeah, you see this
del B squared.
exactly in other graphs, in other regions of the simulation plot. But to approach this quantitatively, you have to use correlation functions, for example, and then you'll see that these two functions are strongly correlated, and statistically they are positively correlated.
Okay. Cool. Very nice. So this was a research note ostensibly done for AAS 236.
Mm-hmm.
Are you looking at scaling this up and doing either an APJ letter or an a full APJ article, or?
Yes, basically, we submitted this at J like a month ago, maybe, and we got the referee report and it was overall positive. So I can say that it is basically going to be published soon.
Okay.
So, and we are actually working on different problems related to this approach here. And as you see, this is extremely important in terms of, for example, if you look at observations, you see this in the solar wind, and also on the solar surface. When we see very complex magnetic field patterns, then it seems that magnetic field relaxes to a low energy state, which is kind of compatible with this picture. We are also working on the topological properties of this and topological theory related to this. I mean, we can define a metric topology for the magnetic field and relate it to second law of thermodynamics and so on and so forth, but it's a different story, basically.
So the future is fairly bright. Is there stuff coming from the Parker Solar Probe that can be useful for this work?
Well, I guess so, but I'm a theoretical physicist, so I'm working with simulations and also theories. But I believe that yes, you can test this methodology, basically the theory, using such observational data and other similar data. But we need people that can do this in practice, and I hope that we get some positive results from there. And in that case, it would be I guess, a revival of Parker theory and its connection with reconnection theory, stochastic reconnection theory.
Cool. Sounds like there will be some good work coming up on this in the next several years. Very nice. Amir, I want to thank you so much for spending some time with us today and describing your research note. And for those who are interested, go ahead and reach out to Amir. And if you're in the game, you'll know how to get him. But we won't be putting his email address in YouTube videos. So thank you very much, Amir, and we'll see y'all in the next one.
Sure. Thank you very much. I appreciate your time, and thank you for having me.
Thank you. Bye-bye, everyone.